I hope you all can hear me. If there's any problem during the lecture, please just speak up. I am not able to see if you raise your hand or something, so just please interrupt me. The same holds for questions. So since we are just 30 people, I think it's still fine if there is some urgent question, interrupt me. I don't want to lose you. So I prefer to have this in an interactive way, and therefore just if you have a question, if something is unclear, please just stop me, interrupt me, and we'll get into a conversation. I'm pretty sure if you don't understand something, there's other people in the audience that also don't understand it. Probably it's my problem then. And the other thing is I tend to speak faster and faster if you let me. So interrupt me to not have that happen. Right. So first, organizational stuff. Concerning this lecture, like I want to fix the date for the next for our next meeting right now, because now you're all here. And I have already written this in the Reddit post. So my constraints are that I have time on the weekends. This is Saturday or Sunday. The earliest possible time I'm comfortable with is 10 a.m. and the latest one would be 9 p.m. I won't move out of the time zone, so it's Berlin time always. And we'll have to manage somehow around busy weekends, because like there's this occasional weekend where I'm out, where something is going on, where I can't find the time. Therefore, I think it's best to plan for every 14 days, and then we'll have some longer breaks and some shorter breaks. But we'll on average do it every 14 days. Victor just turned on his camera, which is something I really like while we're talking about organizational stuff, because if I can see your faces, I get a better impression if you can follow or not. If everyone suddenly looks very stupid and questioning, then this means I'm probably lost you all. So if you, I don't force anyone, I can't. But if you happy and it's like a technically possible, then I would appreciate if you turn on your cameras. I do the same. So then we can discuss what fits you best, but since it's 33 people, I think it would take a bit too long to do a round. So I made a doodle, which you can you click that link? I don't think you can click that link, but maybe you can just type it in your browser. You can also do that later. I'll post the link on Reddit after this lecture. We'll do a little feedback round on Reddit. I will post that link there, and then we will evaluate tonight later what the preferences are. This is just a better thing to vote. It's not the Reddit limitation of just one vote. You can vote for every time slot that fits you. And then I guess we'll do this every lecture. We find the next slot which fits all the people best. And I also try to make it such that the people that are in the lecture get like a more important vote, because I hope for kind of continuity, because the lectures build on each other. Are there any questions regarding this? If not, then I would move on to the goals of this lecture. So this was kind of built as a lecture for an audience at the university, audience of master students at the university, I must say. So I assume that you have a basic understanding of theoretical chemistry. You should know what a wave function is. You should know what a Hamiltonian is. I will do a quick, very brief recap of Hartree-Fock theory, because it's kind of the basis. You don't really need it for density functional theory, but it's kind of the historical basis in which it has evolved. And therefore, most of the explanations of density functional theory make use of Hartree-Fock theory. And then eventually, when we talk about more advanced functionals, then Hartree-Fock theory also just plays an important role as itself, because we use these kind of mixing approaches where you mix Hartree-Fock theory, Fock exchange, and density functional exchange. Therefore, I'll start with that, but it helps if you have heard of Hartree-Fock theory before. But based on this knowledge, I hope that this lecture will provide you with a theoretical comprehension of the formal basics of DFT. So you should know what a functional is, what it does, why we need a basis set, the numerical basics, but this is not a focus. I just want you to understand from a practical point of view, if you run a calculation, what's going to be the bottleneck? Where do I need to cut down on the basis set, or should I cut down on the functional to run this calculation, right? And for this, you need to know what the bottlenecks are. Like, is it the diagonalization of the Fock matrix, or is it the evaluation of the non-local exchange? So we will talk about the performance aspects of DFT. And then you should know or understand the role of DFT in modern computational chemistry. It's not only there to predict chemistry, concrete chemical reactions, but it also plays a role as a benchmark method, as a test method, creates a lot of data for machine learning these days. So I want to talk about all these applications of DFT. And then, because functionals are such an important aspect of the theory, I think you should be able to understand after this lecture how functionals are developed. It's like, I think even half of the lessons in the original lecture were on this topic: how functionals are developed, what are the philosophies that go in, which functionals are good for what purpose, and how we can kind of test them. Benchmarking is this term. And then these theoretical things should translate into practical abilities, because that's what we all want to do. You all want to be able to run more accurate calculations that you get easily published, because they are, you just have made the right decisions when you've chosen the parameters, right? And I think the best way to learn this is to learn from mistakes of other people. That means you should be able to judge the application of DFT in research. Maybe I'll have some example papers. We can think about something like that. I find a paper and I give it to you in the end of the lecture, and the next lecture I expect you to do a very short presentation. What are the main problems with the application in this work? This is kind of a good way to learn to avoid pitfalls. But finally, what we all want, we want you to be able to make the right choices when you apply DFT by yourself. And then there's one more aspect which might be the most important, and this is infotainment. I really hope you enjoy this lecture. I absolutely enjoy talking about density functional theory. It has a place in my heart ever since I've been dealing with it for the last 10 years. I think it's a very powerful and just exciting thing to think about and to use. And also just to make knowledge stick, it just helps if you like what you do. So therefore, I really hope you enjoy watching this lecture. I'll try to make it entertaining. And feedback is the one thing that makes that happen, or gives us an ability to improve that. So I already mentioned I will make a Reddit post after this round, and then you can give me feedback, or you can just send me the feedback in the Reddit chat if you feel that it's more like a more easy context to talk about. And even here, like after the lecture, I will ask for a feedback round, and everyone will get a chance to talk for a couple of minutes to tell me what they liked and what they did not like, where they could follow, where they could not follow, where they were bored maybe. So I guess you understand where I'm going. All right, is this all clear? If there are no questions, then I would move on to like the first structure. I have a second slide on the structure. This is kind of the text slide, and this is just the first half. And I will always show this in the beginning of the lecture. The solid arrows show what we are talking about today. The kind of faded arrows show what's the topic next in the next lecture, and then we will have a short recap, and this will have another color which will pop in the second time we meet. So today we'll start with some basic context about the theory, like some historical background. I already mentioned this in the Reddit post, and I will tell you who I am and what my background is, because I think this is kind of important. DFT is science, but it's not like the hardest science maybe. So there's some flavors going in, and also some background is important. I guess if you come from a Grimm's school or from a Truda school, you will have different ideas. So I want to give you an idea where I come from, what background I have, so that you can make up your own decision with how you judge what I tell you. Right? And afterwards, we'll talk about the formal basics. So Hartree-Fock theory, I already mentioned it. We talk about how to represent densities. And then we'll quickly move towards DFT. This is the Holmberg-Kohn theorems. I did a quite thorough analysis of them. And for the lecture, I think I will shorten this a bit to get this a bit more practical. Also, we don't have 14 90-minute slots, or at least this would take a lot of time. So I think I will cut this down a bit. But we'll talk about compchem nevertheless and Holmberg-Kohn. And then do functional basic, because this directly emerges from the compchem approach. They started by using the LDA, and you get pretty good results. But then I will show you how to move from the local density approximation to the generalized gradient, what the underlying idea is. I will do a detailed presentation of two very prominent functionals, namely the B88 exchange, Becky's 88 exchange, and the Li-Yang-Park correlation, because they are quite important. B3-Lib is still the most used method. We'll talk about hybrid functionals and the adiabatic connection, London dispersion in DFT, because this is, I think, something that has been overlooked for way too long and is now a kind of standard of every model functional. Then we will do another little round on functional development, where we talk about the modern schools, double hybrid functionals, how to test them, and kind of the aspects of benchmarking. But let's start with me. So I'm Jan, and please just don't say Dr. Muse, just call me Jan, please. I'm from Frankfurt in Germany, where I studied, and I did a PhD in Heidelberg with Professor Droyf. And the topic there wasn't DFT at all. I was mostly dealing with photochemistry in solution and their mostly correlated methods. So Andreas Droyf developed a method which is not DFT for excited states. It's called ADC. And I built a solvent model for this. So my first real programming stuff was about embedding. But because these molecules were big and ADC is expensive, I also started using DFT to kind of get more results, don't have to wait so long. So already there, I started to get in touch with the theory. After this, I moved to Auckland with Peter Schwertfeger, where I studied super heavy elements. So the last row in the periodic table, from copernicium to organesson, basically. And there you basically have no chance but to use DFT, because my aim was to investigate their bulk properties. That means you have periodic cells, you have hundreds of these atoms, and then there's really no other choice. And another thing that really becomes important in these heavy elements are relativistic effects. So I started kind of investigating them, how you deal with the calculation. That means relativistic core potentials. I made some myself to do non-realistic calculations. So there it already was lots of DFT. And my last station in the academic career was Stefan Grimme here in Bonn. This is where I'm now, where I developed this R2scan 3C method. I've mentioned this a lot in Reddit, so I guess you've heard about it. If not, then it's about time. I also worked on DFT D4 and semi-empirical methods. And this is, I think, the biggest impression of my understanding of DFT came from my time with Stefan Grimme, because he's really out there at the front doing DFT research, developing methods. XDB is from him, and this has changed my workflows by a lot. Okay, any questions? Not yet? So then let's talk about you. To get an idea how you, or what your idea of this lecture is, because this is I don't know how often this has been done before. I think you're from all over the world. We have another question for this right now. But the first thing I want to know from you is the three most important things you want to learn here. So if you want to learn about basis sets, please don't write I want to learn about basis sets, just write basis sets. We need we need bullets, right? So that everyone types in the same thing. And you kind of go to this QR code and just enter this, and then I hope we will see this. I think now I have to stop sharing for a moment to get my mouse back. So we are already building a nice word cloud here.
I think it will be a little bit biased because you said functionals and then everybody's put functionals and also basis sets.
Did I say functionals? I think I said basis sets.
Oh yeah, sorry, basis sets.
I tried to bias this away from functionals, but this is what usually, at least the 2 times I gave this lecture in Regensburg, we got the functionals first. But this is really the typical order that evolves now. Functionals are the magical thing about DFT. So it's not a surprise that all of you guys are into it. Thermochemistry is obviously also very important because this is kind of the biggest go-to application, I would say. But I think we are almost done. So, 20, 20, 23, 25, still entering more. Nice, everyone contributes. But I guess the outcome won't change anymore significantly. I will go over this and evaluate it next time. We will talk about the results. And I will see if I can maybe adapt and the lectures a little bit. So TDFT is something we probably won't talk about. I see TDFT there. The thing is that TDFT and photochemistry is so different from DFT that it needs its own lecture. That's just a reality. Maybe we can do a kind of excited state intermezzo, but I wanted to do that before, but I didn't. So let's see.
That'll be the follow-up to the successful series.
Yeah, maybe. I have no idea where this goes. I thought maybe I'm alone here with 3 other people and I give a lecture, but no, there's 40 people. If you show up again next week, and I think this thing could evolve into something where we do a lecture, photochemistry or rewired. Yeah, this is maybe a bit extreme, but I like photochemistry a lot. So I mostly did photochemistry. I work in a company that does OLEDs, so photochemistry is my thing. I'm with you. Okay, but I guess we have a good overview now. And, so this focus thing is annoying. So the next thing I wanted to see, I need to stop screen sharing again. Man, this is annoying stuff. Whoop it up. So you can see it again where you are from. I see some people with a coffee there, which I guess means we have people from the US. Here in Germany, it's almost 4 Uhr, Zeit für ein Bier. I'm drinking water though. Oh, so we have India, we have China. It's gonna be late at your location, guys. Most is Europe so far, which is not surprising. Maybe it's a bias in the timing. We have Southern, we have Brazil even. Okay. Is this 11 in Europe, is this all Germany? Okay. So I think we have a clear focus on Central Europe and Germany, if this is the case.
Can you show the map?
Yeah, sorry. I forgot sharing this. This confuses me. Sorry there. Now you see it, right? This is exactly what I mean. Remind me of these things. I don't notice them. Even after 10 years in academia, when you're in lecture mode, you have a bit of tunnel vision. Japan. What is this below Japan? It's Guam. Do you have people on Guam? Or is it just a misclick on China? Okay, interesting. So we still have, despite this Euro bias, it's almost around the globe. Nice to see. But before I bore you with more of that, I'll post a final map in the Reddit. Okay, and this is kind of a repetition from what we had before. It's more like a storyline, how I plan to put the red line into the topic, and the beginning, which is today's lecture, is really mostly, okay, chemistry is really just quantum mechanics, because we know all the equations. It's just too hard to solve them for actual relevant problems. And so Homberg and Kohn came around this time when this was recognized, like, okay, the wave function is the problem, not the quantum mechanics. Just don't care about the wave function. Let's do it with the density, because this is just 3 dimensions. It's much simpler, not 3 n dimensions. And the Kronberg and Sham, now I'm confused. Kohn and Sham recognized this and said, yeah, kind of, but there is an issue, because if we just deal with this density thing, then we don't know how to get it. Like, how do you optimize the density? So they said, well, yes, we need a wave function, but not a real wave function. Let's just make our own nice and simple wave function with just non-interacting particles. And then all the rest, all the complicated stuff, we put into this one exchange correlation function, at this time LDA. And this actually worked much better than trying to do the wave function. I will talk about this in a minute a little bit more. But then they also realized that the LDA is, it's kind of obvious that this is a very rough approximation. If you do LDA, local density approximation, means your densities like uniform electron gas, and molecules are not like that. Molecules are actually very different from that. So the next logical step was to take account of the density gradient. So if the density is strongly increasing or decreasing, perhaps the electrons will move a bit differently. And then this was already the key to getting thermochemistry right for molecules. People at that time were doing like these atomization energies, and all of a sudden with BLIP, for example, or with PBE, you were able to calculate molecular energies of formation with an unprecedented accuracy in very little time. And the next big step in this direction was the idea of the adiabatic connection, where it was Becke, but it was also some other people. But Becke was really the first to say, well, let's just mix some of that real Fock exchange into our fine and local GGA. And this was the breakthrough, because this is when not only thermochemistry, but also barrier heights and other properties suddenly were much better than with wave function theory. Even MP2, which was kind of the competitor at the time, was suddenly not always the most accurate one. There were still issues, but the hybrid functionals were really the point where DFT took off. And then there's a fifth step, which this is again kind of one of these flavor things. You could put a lot of things here. I think up until the hybrid functionals is pretty clear, but I think coming from the Grimme school, the next important thing is that we need to correct long-range correlation, because this is something that's missing in DFT. If you do GGA, even in hybrids, you don't get the correct long-range correlation energy, because you need excitations for that. And this is not a problem if you have 10, 20 atoms, you can survive it. But if you want big molecules interacting, or just one big molecule, then there's a problem with the asymptotics and non-covalent interactions. So the fifth important step is, in my opinion, to realize that you need this long-range correlation, dispersion corrections, essentially. This was around the 90s already. 2000s, something like this. And on these last 3 points, the last 5 points, I have 2 more, are range separation. Because then it was recognized that you have some things that are better with lots of Fock exchange and some that are better with little Fock exchange. But if we don't mix this in with a constant amount, but make it distance dependent, then we can get kind of the best of both worlds. This turns out to be very important for robustness, for excited states. And you can think about this as an analog to the to this part here, because here we restore the long-range correlation part, and here we restore the long-range exchange. And the exchange and correlation are very important in DFT. Then you have, this should be number 7, or this is, sorry, both of them are in the 6th lecture. You mix in not only wave function exchange, but also wave function correlation. These we call double hybrid functionals. They are the most robust we have nowadays, but this also comes at a cost, right? So now all of these 5 points here are where we stand today in modern modern functional development. So this is the most important point as per your request. We will have another lecture then kind of to put all of this together, where I will kind of give you this overview from the very fundamental functional development in the School of Purdue, from, for example, PBE, scan, TPSS, PBE0, where these functionals, the people try to make these functionals without any empiricism. We don't fit to any reactions, maybe some rare gas atoms, but it's mostly really based on constraints. We know how the density should behave in this situation, which is kind of artificial, but we make our functional fulfill this, and then suddenly it also works for molecules. And on the very opposite side, you have this highly empirical approach of Trula, which in M06, I guess he put 42 parameters, and then he had the big database, very important work, by the way, this database stuff. And then we just fit all of these parameters to represent this huge amount of data points. It's a bit ML already, but 10 years earlier, which also gave very impressive results. Like the M06 was for a long time the best global hybrid function. I think it still is to this day, M06-2X. And in between these two extremes, you have Becky, Head Gordon, Martin from Israel, and they kind of mix empiricism with some fundamental approaches. For example, Head Gordon in his omega B97 family of functionals, most of you will know them, I guess. They said, well, we have parameters, but we increase the number of parameters until we don't see an improvement in the RMSD anymore. So we only add, we have a test set and a training set, ML again, and we only make the number of parameters so big that our improvement on the training set no longer translate into an improvement in the test set, because then that's overfitting. So they, for the first time, thought about things like that. We will talk about this in much detail. And very important in this context is how you benchmark or how you systematically improve these functionals. Because by definition, as opposed to wave function theory, where you can just say, okay, I do triples if the doubles are not enough, or quadruples, but you can't do this in DFT. You can just include hybrid fork exchange, and then you can do a double hybrid, but nobody tells you that your double hybrid is more accurate than your GGA. Right? So it's not systematically improvable, so you have to improve it systematically. How do you do that? And the answer is testing, benchmarking, and there's some issues with references. Where do you get them from? The statistics become a problem. Robustness becomes an issue. So what is it? Do you want a niche functional or a globally applicable one? These aspects we are going to talk about. And then finally, I had 2 more things in the lecture I made for the Uni Regensburg. And this was one excursion into periodic systems and solids. I don't think we're going to do this. I haven't seen it in the poll. And I'm still wondering if exercises are a good idea. As the big issue with exercise, everyone needs to set up the same program. I would say Orca, and then I would hand out like little tasks. One task was design a Lewis base with maximum 5 atoms that should be as strong as possible, and then do this by changing the functionals to increase to kind of get them to overbind. So I have some things like this, but I'm still not convinced that this is a good idea in this context. Maybe we'll talk about this later. But for now, let's move on and start with the actual lecture. Are there any questions regarding this part? Anything you miss on the slide? If not, then let's jump right in and motivate why we want to use DFT. I already gave a little overview of that, but now let's dive into this. And this is a paper, or an abstract to a paper by Dirac from 1929, and which is, it could be the motivation of modern DFT. So the nice thing is he's a quantum chemist in the time. Quantum mechanics has just taken hold in science. And he writes now, and the general theory of quantum mechanics is now almost complete. The imperfections that still remain being in connection with the exact fitting of the theory with relativity ideas. So he's working on how to combine Einstein's relativity and quantum mechanics. These imperfections give rise to difficulties only when high-speed particles are involved and are therefore of no importance in the consideration of atomic and molecular structure and ordinary chemical reactions, in which it is indeed usually sufficiently accurate if one neglects relativity, variation of mass with velocity, and assumes only Coulomb forces between the various electrons and atomic nuclei. So this is what this paper is about. And he assumes that relativity has no impact in chemistry, which was wrong. He made one mistake. We'll talk about this later in the lecture. The mistake he made is that core electrons don't play a role for chemistry, which is kind of understandable. The problem is that these effects trickle down, and the valence electrons change if the core electrons change. And therefore, it is, in the end, very relevant to chemistry, but this is not what I want to talk about. Finally, the last paragraph is really the important one. The underlying physical laws necessary for the mathematical theory of large parts of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be solvable. It therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. So this is the perfect motivation for DFT in 1929. We just need good functionals or good approximations, right? But also at the time, there was still Schrödinger with the Schrödinger equation, and this is kind of the main equation which he was talking about, the non-relativistic one. It gets even more complicated if you want to make it relativistic. But now this is just the Schrödinger equation, the Hamiltonian of the Schrödinger equation, of the molecular Schrödinger equation. And what you have here is the the kinetic energy of the electrons, the electron-electron interaction, kinetic energy of the nuclei, nuclear-nuclear interaction, and the electron-nuclear interaction. Right? And then at this time already, Born-Oppenheimer was a thing, so we can forget about these nuclear-only terms. We just have to, this is just basically a constant, and we just have to think about these. But if you write these terms down for benzene, small molecule, 42 electrons, you end up with a Hamiltonian with 126 base and 42 spin coordinates. Right, so the electron-electron interaction in there, this little beast, is a many-body problem. And you can solve this even for 3 particles. We have here 42. So in 1929, there was not even hope that this monster can be solved. This is what he said, what he meant when he said, we know all the equations, so we can basically write the Hamiltonian down exactly, but we have no clue how to solve this monster of the equation. What good approximations could we use, right? And now we jump 30 years in the future. It's in the 1960s. You have the first approximate calculations for benzene in the literature with the Hadrey-Fock theory. And there are very early correlated methods where you do multi-configurational SCF, CI, or Miller-Placid perturbation theory, what we nowadays know as MP2. But it's very approximate. Right? And these calculations take a long time on, I think in the meantime, it's no longer mechanical computers, but they had actual electronic computers. But still, people recognize, well, maybe we need these better approximations, right? We just need a little bit more. And then these three guys were working on the problem, and they recognized, first of all, and that's the first Hunger-Kung theorem, there is a direct and unique mapping between the wave function and the density. Right? And what this means is, if you have the density, which is much less complicated, there's only one wave function where this density can come from. And this is kind of the underlying foundation of DFT. And then there's one more ingredient, which is very important for the numerical side. So if you want to be able to tell that you have the best solution, or that my solution for the molecule is better than the one that you just came up with, then you need some criterion. And the criterion, and there's one very simple criterion, and that is, if your method is variational, then you can say the lower energy is the better one. Very simple. And this is very important. And this is the same in wave function. It's the variation principle, which tells you, if you put your wave function, your Hamiltonian, your basis function, you change them a little bit and the energy goes down in Hartree-Fock, then this means you have improved your description of your system, because the best description, or the true description, is the one with the lowest energy. And so with these two cornerstones, they went ahead and said, well, okay, now we have now a theory which in principle allows us to calculate molecules, but there was still the problem of doing the calculations. Like, what are the actual numbers to put into computer? And as I just told you, they already had Hartree-Fock at the time. So they had self-consistent field equations. They had programs that could solve these equations, but not for DFT. And compchem, you can see, very loosely spoken, as a way to put DFT into the technical machinery that was at the time developed for Hartree-Fock. It's a practical approach to calculate the density in analogy to Hartree-Fock SCF. And one key ingredient, because in Hartree-Fock you have a wave function, and I just told you, I think 2 or 3 slides long, that the wave function is the problem, and we need to get away from it. They introduced this. They reintroduced the wave function, but they don't say it's the real wave function. It's just a helping construct, which now you can formulate this in 2 ways. You can say, well, it's a construct to help me use Hartree-Fock technology to evaluate DFT, or you can say, well, it's a theoretical construct that tells me where I can get my density from. Right? And the key difference between these theories isn't, it's not a different problem. It's not at all that much different. There's one issue which is the main difference, and which is important. And if you take home one thing from the lecture today, then it should be that. In compchem theory, you have a single determinant. And this is okay because it's a non-interacting system. And this single determinant is fine because we postulate we have a non-interacting system that creates us, if we use this magical exchange correlation functional, the density of the real system. So the approximation in compchem DFT is in the Hamiltonian. We say we make an approximate Hamiltonian in such a way that one determinant is enough. You start with the Hamiltonian and then you go, okay, then we can use this very simple one determinant wave function. In Hartree-Fock, the whole approximation of Hartree-Fock is that we know we have this complex monster of a wave function. We don't know really how to solve it all at once. So let's start with the simple assumption. We use one determinant in the mean field approximation. That's the name for it, for using a single determinant. From the single determinant, it emerges that you do this Coulomb and exchange treatment of electrons, which is mean field theory. And this is just a starting point. And then afterwards, we do correlation. We build on this single determinant and later add more, but we need the starting point first. And here the approximation is therefore in the wave function. Because in Hartree-Fock, all the approximate stuff follows from the assumption in the beginning, let's just use one Slater determinant for the wave function. So it's not just a different view of the same result, of the same issue, it's a different approach to the same problem. And in that time, again, technically, it was very clever because you recast that problem of getting the density and optimizing density in a way that technology that existed already can be used for. And another very important point at this time in the 60s, 70s in physics, people were already busy with the unified electron gas. This was known because they were studying metals and conduction and stuff like that. Fermi and Slater were very prominent in this field, and they basically came up with a way that describes how electrons, what's the energy of an electron interacting with other electrons if the density is constant in my area. This is a very simple model for a molecule or for a metal, for the valence electrons of a metal. And you can write this very simple formula, basically take the density to the power of 4/3 and then integrate over space. Kind of very, very simple, but it works good enough. And now there's something broken, but this, say you can do the same for the correlation. It's a bit scaled, but forget about it. The important thing is this picture. So this shows you the absolute distribution of density in a water molecule. And you see immediately that this is not constant density. You have this kind of cusp at the oxygen because this has a 1s electron and has a higher shell. It's cut out here. It's a very old picture. And then you have the hydrogens here, which just have some density, but in between the bonds, for example, the density varies. Everywhere in this molecule, the density varies. You need to make the point very small until you have the feeling that the density doesn't vary. But still, with this approximation, which intuitively you would say does not really fit. Now I have to restart this because we need to see this table. Can you see the table? I guess you can see it good enough. So with this very basic theory and this very crude approximation, you could go into these very simple molecules, kind of think of it as a benchmark in the 60s, and calculate bond length, which were suddenly in much better agreement with the experimental values you had than Hartree-Fock theory. So basically, out of the box, this very simple theory was able to beat the established method in the field. Let me hope that, okay. Here it's all good with the pictures again. And one, nowadays, we don't have the LDA. We have a couple of more functionals. There's so many magical functionals nowadays. So all on the x-axis here, you have lots of functionals, and here you have an error estimate. And this is not trivial how to get this number. This is part of the benchmarking lecture because this is a big benchmark. It's called the GMTKN55, the General Main Group Thermochemistry and Kinetics and Non-Covalent Interactions 55 database, 55 subsets, 1,500 energies, and you have very accurate wave function theory references. So somebody sat down and spent a lot of computer time to calculate coupled cluster perturbative thruples for all of these molecules. And then you plot basically the error against this reference on the y-axis. And these functionals are sorted here. So we have some house numbers first. Hartree-Fock, the theory at the time I just told you about, has an error on the set of 25. So it's basically twice this scale. It goes through the roof here. Then DFT LDA, the method, the very first try, just use this silly approximation just to see how it works at all, or if it works at all, immediately beats that by a factor of 1.5. So you end up with 16 kcal per mole. And the kind of best method at the time, I would say, which you could afford in the 60s, MP2, on benzene maybe, has an error of 6 kcal per mole. And this is here, and you can immediately see that there's already density functionals which are better than that. And this is from 2017. So this is already almost 10 years in the past. If you check the GGAs on the very right here, they approach about 8. So GGAs already are close to what you can get today with MP2. The meta GGAs, there's not such a huge difference, just not only the gradient, but there's also the gradient of the gradient in their kinetic energy density. They are not that much of a step up, but R2 scan is a little bit better than scan nowadays, but it's around 6.5-ish. I think there's one Martinet Gordon meta GGA, which is quite a bit better here. I think it's below 6 even. Then you have the hybrid functionals here. With Fog Exchange, they are more demanding computationally, but you immediately see that they clearly beat MP2 already. So if you don't know anything about your system, usually you should rather use Omega B97XV than MP2, because it's not only much cheaper, it's also just from this should be more accurate by 20-30%. By the way, if you have questions, please ask. Nobody has asked a question yet. I'm sure somebody get lost. So please stop me if you have questions, if you want to talk about something else. So we have the hybrids here, and then I mentioned already these double hybrids. We will talk about them later, where you mix also MP2 theory into DFT. This makes it quite a bit more expensive, but you pay this cost the same as you would pay for an MP2 calculation, but you get much better results. I think the best double hybrid nowadays, this is a revised version of these DSD function hills here from Jan Martin in Israel, and they have an WMT-MAD of 2, I think. So they are 50% better already, and the best hybrid functional is Omega B97MV, so it's a direct successor of this thing, and it's about 3, I think. So there has happened quite a bit. If go down 1 kcal per mole here in this era is quite a big achievement. It's not that easy. You need to improve a lot of systems, but it's very easy to improve one aspect of a method. But because you have these 1,500 energies and it covers 55 subsets with vastly different properties, you have to usually, if you improve one thing, you sacrifice somewhere else. And this is not something that works here. You need to be better on everything at the same time. And this is much more difficult than tailoring a functional a little bit more into one direction. But so we will use this a lot to judge how well these functionals are, to give you a number for all these methods we discuss. I will just tell you this has 7 on the WMAD 2 for GMTKN 55. This is just a nice house number we can use to talk about this stuff. And then people make funny pictures because in DFT we have this kind of ladder where we increase the complexity of the functional, and I think Purdue came up with this idea of making a Jacob's ladder, which is some biblical figure. You start on a Hartree hell or in a Hartree world down here, and you move towards the heaven of chemical accuracy by including more and more complex ingredients in your functional. Yes, I don't know, 5,000 different representations of this. One of my students in the Grimme group made a really nice one. I thought I included here, but I forgot about it. And this is the GMTKN 55 review article version of it, where you have like the best functionals of each rung here. You find many of these, and now you know what they are. Okay, is this all clear? No questions.
I have one question. Could you go back to the previous slide?
This one?
Yes, I actually did not really understand completely what was the difference, because, for example, if I try to see it from the Schrödinger Gleichung that we had there, like I understand that you have the pure Schrödinger Gleichung, and then from there you say like, you know what, for working with Hartree-Fock, what I am going to be doing is like I'm going to actually modify the Hamiltonian. So I will have my Hamiltonian for the single functions, and then I will just have a potential, which is this mean field. This is just like basically Hartree-Fock, right? And then when what I understand is what you are doing is like you are simultaneously working in a different Hamiltonian and working in a different wave function. Now, when you go to this DFT formulation, I was a little bit confused on the way that you actually wanted to draw this axis parallelism between Hartree-Fock and compchem, because I really did not see.
So in Hartree-Fock,
yes,
you have for benzene 42 electrons, and you have this wave function in principle, not in the actual theory, not in compchem DFT, but from a fundamental point of view. You have to deal with every single electron, because every single electron has 3 space coordinates and 1 spin coordinate, right? And with this, you end up with 176 space and 42 spin coordinates for your simple benzene. And if you want to deal with the density of benzene, if you just think about benzene from a DFT point of view, then it's just a cloud of average electron probabilities. And the only variable you have is one X, one Y, and one Z. And then alpha and beta, the spin. And you can say, well, at point X, Y, Z, the density of benzene has a value of 42 in alpha spin and 43 in beta spin. So you just have much fewer variables you need to describe your system if you just think about the density and not about the probability or the density of each electron, right? You basically go from every single electron to the average to find any electron here, because electrons are indistinguishable anyways. So it doesn't matter which one is at this point. Do you understand this now better? Was this the question?
No, but this is actually quite nice. No, I just wanted to go again to this next slide, I would say.
This one?
Yes, this one. And I think, for example, you have also the Hamiltonians down for compchem and for Hartree-Fock down. So I do not know if you could actually just make the connection to try to see the difference between these two.
The Hamiltonian for Hartree-Fock is the exact one. In Hartree-Fock, you have the real non-relativistic Hamiltonian. If you just put this Hamiltonian to the actual wave function, which is not a single determinant, but it has all the exact determinants, you go to full CI basically, you create all possible excitations, you plug this Hamiltonian in, and you get the exact real answer. You get basically the analytical, not the analytical, but the numerical exact number for the energy of your system. If you do this with the DFT Hamiltonian, you don't. Because in a DFT Hamiltonian, you don't have the exact Hamiltonian, you make an approximation. Right? In the DFT Hamiltonian, you don't have Coulomb and exchange, like it comes out from the derivation you do in Hartree-Fock. But you have Coulomb, yes, and then you have some exchange correlation potential, which you decide how it looks. You say, well, maybe my exchange and correlation energy just depend on the average of the density, the number 42 in benzene at this point. And then at this point, the density is a bit different. The value is 36, and now I have a different energy here. And then you integrate over all of these, and then you get a value for the energy of benzene, which does not depend on each single electron, but just on the average density. So, and therefore, the approximation is a different one. Here, you have the exact Hamiltonian. There's no approximation in Hamiltonian, but you say, in Hartree-Fock, I just use a single determinant. And if I use CASD, for example, I just use the all single excitations and all double excitations. So I have a couple of thousands of determinants or hundreds of determinants for benzene, but it's still an approximation. But the Hamiltonian is exact. In DFT, you never go over the wave function. The wave function is not really existing. The wave function in DFT is just a technical tool to calculate the density. This is compchem DFT. Right? This is not Hohenberg-Kohn. Hohenberg-Kohn is just, okay, the density, and then people were not sure how to use it, but to use it, you go to compchem, where you make something very similar to Hartree-Fock, but you don't pretend it's the real thing. That's why it's not an approximation. You say, well, you can actually show that from this artificial test systems, if you just put in the right functional, you get the exact density. Even though it's just a single determinant and it's approximated. But it's not, you don't claim that the wave function is real. You just say it's a tool I use to give me the density, because I can't get it otherwise. Is this a bit more clear now?
Yes, thank you very much.
You're welcome. Any more questions? If not, then I would move on. We talk a lot about energy. We just talked about energy here. Here, it's a deviation of energies we calculate. But I thought it's kind of important if we talk lots about energy, about correlation energy and Coulomb and whatnot, that I give you an idea what the typical size of these numbers are for benzene, because it's a guinea pig of computational chemistry. And what we have in terms of energy in such a Hamiltonian, or the Hamiltonian just gives you each energy contribution of all of these interactions, and we categorize them usually as the one electron energy. And this is the easy one. It's covered by Hartree-Fock, and it's exact in the term in Hartree-Fock, also in DFT. You just have the electron-nuclear interaction, so how close each electron is to the nuclei and to how many. You have the kinetic energy, which is actually a bit difficult in DFT. And this is more or less trivial. And then you have this mean field two electron interaction. We will talk about this in more detail next lecture. But in Hartree-Fock, you have basically idea to split the electron-electron interaction in two parts. One is the one that is not in Hartree-Fock. This is the explicit one, each electron with the other. But you can do a DFT-like Hartree-Fock way of dealing with electron-electron. And this is, you just check how one electron interacts with the average probability to find all the other electrons at this point. And this is actually where the exchange term comes from. And this is not trivial. This is easy because you can do it just with one determinant. And it's the classical Coulomb interaction. It's really just electrons repel each other, electron clouds do the same. And you have this quantum mechanical effect, which comes from the antisymmetric nature of the wave function. If you just plug in the Coulomb interaction, then all of a sudden, if you do the derivations with a theta determinant, then you have two terms. One is this really looks like the Coulomb, and then one is weird and looks like the exchange. And this is a direct consequence of the quantum nature of molecules. And in Hartree-Fock, it has an important role. We'll talk about this later. But this is the easy part, and then there's this difficult part, and this is the explicit electron-electron interaction, where if I have an electron here and I wiggle with it a bit, all of the other electrons will feel this, right? And this correlation energy is also a quantum effect. We call this instantaneous or explicit electron-electron interaction to discriminate it from the averaged one. And this is the difficult part. This is where what you need the MP2 or the full CI for, which takes a lot of computer resources. And in DFT, you just approximate it with this exchange correlation function. Now you can plot these different terms for benzene. I run a Hartree-Fock calculation in benzene. I think a DFT calculation. Then you can see that you have minus 231 total energy of benzene. Anyone has an idea what this number means? What this energy is? If you do a DFT calculation for some molecule, you get a number. What's this number? What does it mean?
Hartrees, right?
Yes, the Hartrees is the unit. But what's the physical meaning? Like if I roll a ball down a slope, then I can calculate the energy difference, right? So what is the energy difference of 231 electron Hartrees? What's the situation? What's the other situation?
The energy you'd have to put into the system to separate all the electrons and nuclei to infinite distance.
Perfect. Exactly. So the energy you calculate, the total energy of your molecule, is everything at infinite distance. You pull it together into one place in the configuration of your molecule, and you get 231, minus 231 Hartrees. So in this is minus 713 one electron energy. So this is much bigger. And then we have the kinetic energy of the electrons, because they move, they need some energy to get moving, so to say. That is costs a bit of energy. And then you have the sum of those two is the one electron energy, and this is always negative. right? And then you have the 2-electron part. This is just a simple one, not the correlation energy. The correlation is in there. So we're talking here about 279 total. Of that, we have 313 Coulomb. So this Coulomb energy is significant compared to this and that. But now comes the funky part, the important stuff. The only difference between two DFT calculations is basically the exchange and correlation energy. And this is just 35 and 3. So you can't even see the correlation energy here, and the exchange is very little. You have these huge energy contributions in the molecule, and there's just a tiny part that matters. Right? So this is important. Right? So to get this tiny, almost invisible pink bar here, you have to spend much more computer time than to get all the rest. This is one way you could see this. Now I think now we can do it. So what are the implications of this? So we have this huge energy contributions which cancel each other out largely, and then we end up with 231. And now let's put this in the context of chemical interaction energies, because that's what we all want to do. We want to, I think most of us are chemists, so we want to investigate chemical reactions. And in a chemical reaction, you have 0.05 Hartrees, which is 130 kJ per mole. This is a typical chemical reaction energy. So this is much less even than that. If you have typical isomerization energies, you have 0.01 Hartree, and the typical conformational energy is 0.001 EH. So these are tiny compared to these huge chunks we have here. Why is that important? Well, if you want to calculate these and get these numbers right, you need to get all these beasts right. And to get them right, and you need to get them exactly right. Because if you have two sides of a reaction, and on lots of this will cancel out, but if one side you deal with one of these huge terms in a slightly different way and just do 1.1% difference, then you have a huge imbalance in your energy. So this means consistency will be very important. Then there's another good way to think about this, which is this picture. So we want to measure, like calculating a chemical reaction is like measuring the mass of this guy, this tiny guy. But in which way do we do it? Well, we don't do it directly. This would be much too easy. We take a ship and put him on it, and then we take him off of the ship and take the weight of the ship. This little guy is your conformational energy. You want to calculate it exactly. And then you have this 700 or 1,000 Hartrees that is just this ship, which is all the other stuff. And you need a really, really good scale to get an accurate reading of the mass of this guy from this experiment, right? And this is what we do, right? So if you want to get thermochemistry right, people say you need chemical accuracy. It's 1 kcal per mole. This you get from this gold standard method. So in wave functions theory, I already mentioned this, things are systematically improvable. So you can say, well, at this level, I always have an error that's not larger than this for a certain subset of chemistry. And for accurate Boltzmann populations of conformers, which determine the properties sometimes. Maybe two conformers have vastly different properties, and you need to get the energy right down to 0.1 kcal per mole. Right? So this is nothing compared to the vast energy differences, and this is kind of symbolized here in this picture by the ship. So you have to use exactly the same ship in each, and you have to do the integration the same way. There's lots of requirements in consistency. If you don't get consistency right, then you can forget about your DFT calculations. And this is one thing. And because of this, like DFT can do this surprisingly well. Much of this is error compensation. So you don't get, if you look at any single of these bars, you will presumably do quite a big error in every system you investigate. But because the error is very consistent between products and educts, they cancel out. And this is why with DFT, this weird experiment works and why it's so successful. And if you want to talk about kind of success of DFT, how I think today chemistry would not be, it would be difficult to imagine chemistry without DFT nowadays, because everything we do is based on modeling. Either before we do the reaction, we screen for options that actually work to save time in the lab, or we do an experiment, we don't understand what happens, we look at the calculations to get an idea. And because of this, the number of publications and citations of kind of the DFT papers exploded in the last couple of years. And you could say, because of the success, DFT has become the workhorse of compchem. So most of the work is DFT. There's still wave function theory stuff, but it's not that big. Because of this success, there was a Nobel Prize in 1998 to Walter Kohl and John Popel for the development of density functional theory and for John Popel's development of computational methods in quantum chemistry. John Popel, you all know him from the basis sets, I guess. He did a lot of the important work in the early days. Yeah, let's skip that. And now there's one more aspect I want to take you through. And this is kind of the role of DFT in modern research, because DFT has a special place. If you look at this, unfortunately, this is German and I had no easy way to translate it. You can think about it like that. So you have the number of atoms on this axis, and we have the number, the simulation time on this axis. And if you're interested in a few atoms and femtoseconds, you can do electron dynamics, right? This is all of quantum mechanics. DFT, wave function theory, it's all down here. Wave function theory is a bit more down here, and wave function DFT is a bit more towards this direction, right? And then you have these continuums models, mesoscopic models, and molecular mechanics, force fields basically. And DFT sits here at the interface between highly accurate models and these force fields, these more approximate force field models, right? So DFT connects these two regimes. And because you cannot directly connect those, because there's no systems where these overlap. And in one study I did 5 years ago nicely illustrates this problem. And this is the last thing I want to present today. So I will give you a little bit, I'll basically present this paper to you. I mentioned it already in the Reddit. And I think this nicely illustrates how DFT connects all these theories. We used most of these things here, like the first three in this study, and DFT really worked as like the connecting point, the pivotal point to connect the other theories. And therefore, let's dive in this study. Something is wrong with the animations here. And the paper is a reply or comments in Angewandte on an original article. And in this original article, what they did is they made this crazy molecule here, which has a tellurium-nitrogen interaction. And this tellurium has a sigma hole, right? You have this very electron withdrawing group on the right. And this kind of creates a hole on tellurium on the other opposite side. And this nitrogen donates its density in here. And then therefore, this interaction is very it's a weak interaction, so you can control it by temperature. And what they did in the study is they measured the crystal. And from this X-ray measurement at 100 Kelvin, they got a tellurium-nitrogen distance. And they found that this forms like these dimers. And then they also did, and this is why this is funky, this is what Norbert Mitzel, it's like one of his main topics is, they did a gas phase electron diffraction experiment. You can evaporate this and you get a sufficient concentration at 445 kelvins. And then you can measure an electron diffraction spectrum off of that. And you get these points here. And the dotted line is, the red line is the fit of that. You see there's some minor disagreement already here. And each of these points, this spectrum, like a UV-Vis spectrum, it consists of small contributions, and each of these contributions corresponds to the distance of two atoms. The electrons interact with them, they get scattered away, and they get scattered the most on heavy nuclei. So all these tellurium peaks here are the largest, especially the tellurium second period peaks with F, with N, with C. But this doesn't, this is a spectrum, but you can already, I had the question, are you sure that all of the distances is enough information in the spectrum to fully reconstruct the structure of this molecule? This is what they did then as next. They went ahead, they used DFT naturally, because everyone uses DFT nowadays, even experimentalists, and they built from this spectrum this structure. So you have the solid bond distances here, and this is the important one, the tellurium nitrogen distance, so this distance, and they found in the solid at 100 Kelvin 2.64. In the gas phase, they measured 2.92, and this is a huge difference, right? This is a ginormous difference, and yes, this value here is back corrected. That means they did simulations and tried to account for the vibrational elongation of this bond. This is back corrected. That means this is the value they assume this molecule to have for this distance in the gas phase without heat. And if the molecule was in the gas phase at 0 Kelvin, this would be the distance. Is this clear? And by the way, now, if you have questions, immediately interrupt me, please, because I don't know if you can follow or how well you can follow. And then in the DFT, here you have some DFT results. You have PBE0, D3, very sound method, still used today, very old, but usually it's quite robust, so it's never completely wrong. And here it predicts a much smaller value already. But they also did another calculation, and they said, well, then this functional seems to work better, right? It gives you 2.9. And there's a couple of things which are really surprising. First, this huge difference between the solid and the gas. No idea where this should come from. And usually you have effects, packing effects in the solid which compress stuff, but this is 0.05 angstrom, not 3.0. This is a lot, right? And again, this is back corrected. This is not including the temperature. Then you have this huge distance between these two methods, and this shouldn't be the case. Usually DFT, this is both hybrid DFT, same functional type. They should give you results within, again, maybe 0.05 angstroms, but not much more than that. This is suspicious, right? And then somehow this is not, both of these things are at the same time. So this is off from PB0 and matches the experiment, okay. So Stefan Grimmer was reading this and told me, Jan, let's have a look. So we ran some quick calculations. Now we have the same distance here, and this is transposed. I'm sorry for that, but here we have the relevant distance, and the solid experimental value is here, and I did R2 scan 3C calculations. This is one functional PBE0D4 and M06-2X, because this is most like this M06, which they used, but in the solid, Fock exchange is the problem, technical issue. So it's kind of just takes more time. So I just did this, which is the Fock exchange free version of this functional, basically. Right, so, and in the solid, you see, well, R2 scan 3C, this method works really well. You see, yes, okay, there's quite a large distance here with this functional, but not as big as the difference that they suggest. And then we did this in the gas phase. So this is the periodic calculation with all these molecules in a box. And this is just the isolated molecule in the gas phase. R2 scan 3C, which gives you basically spot on value here. Also for the other properties, you have 0.2 angstrom deviation. This is strange. PBE is a bit longer, yes. We can reproduce their value here. But this value is very similar to PBE. So somehow their value was odd. We wrote them an email, and yes, it turns out something went wrong. They took the wrong value from the calculation or messed something up. So they corrected their original paper, saying yes, somehow things got mixed up, and this is not really the value. Our value is correct. So there's no DFT support. is what that means for this huge gas phase distance. And then there's another thing that's important here. These are the methods down here. This is semi-empirical methods, XTB. This is basically between DFT and force fields. You have something which is 1,000 times faster than DFT, but not so accurate. And these methods all give you much shorter distances here. Like just look at GFN2 and GFN1. GFN1 is the method they use. So this method gives you a much shorter bond length here. So why do you get such a shorter bond length? So we can take a look at the potential energy surface. And what I have here now is this distance here in X, and in Y we have the energy. So this is a potential energy scan. You see in black we have this wave function level, this very highly accurate stuff. And in red we have R2 scan 3C. This is that method. And you see, yeah, well, it's basically 1,000 times faster. It just takes a few minutes to run this scan with R2 scan 3C, but you basically get the same result as with this highly accurate method. All the DFT methods agree mostly. Only these GFN methods, they are much deeper potentials, like almost twice as deep, and also much shorter, like the GFN1 here, somewhere there. So and then if you zoom into this area, you can kind of see that the scans are consistent. Is everybody understands what this means here until this point? So there are no questions. So I guess I can move on. We have good energy agreement. We have good geometrical agreement. We found that GFN overbinds. And now with this, at this point, we were convinced that it cannot be that this molecule in the gas phase has such a large distance here. Just not possible. This value is converged for sure. This is you can do more accurate calculations, but usually they never have such a huge impact that they would move this from 2.67 to 2.9. Also, all of the DFT functionals, which usually they agree with each other. Everything is much shorter than 2.9. So what could be wrong? We took another look at their work, and then we checked how do they correct for these final temperature effects, because they did the experiment at very high temperature, 450 Kelvin, but they give the value for 0 Kelvin. So this correction is not trivial. So if you can plot this, right? Temperature is nothing but an energy. You can just plot how much energy 445 Kelvin corresponds to with respect to the minimum energy surface that we have. And if we use this coupled cluster surface that we got and put in the amount of energy that atoms have at 445 Kelvin, you can see which range of the potential energy surface is accessible. And what's accessible is this range, right? Yes, the molecule can be at this large distance of 2.9, but the average won't be there, right? So you get maybe, if you put the population here, it's not maybe not to the lowest point, but the average moves a little bit to the right because this part is more steep. So you get like an asymmetric stretch, but nowhere near what they suggest. So what they actually did is, like what they wrote, was wrong. They corrected this again, but I don't want to bother with this. So they used this GFN1 method to calculate the bond stretch at higher temperature. And as you see here, GFN1 really overbinds this. The minimum is much too low. And if the minimum is too low, then this means nothing but that your temperature is also too low. So they basically undercorrected this distance. So we did calculations with this GFN1 at the temperature to see what the correction is, because they didn't explicitly give it. So we simulated these systems at 445 Kelvin, at 0 Kelvin, and just formed the average bond distance, and you get a value of 0.05. Right? So with this means their real measured value was 2.96 angstroms, and they corrected this to 2.91. But if you use a different method, one that doesn't overbind, like this blue method here, which is very similar to this high-level result, and you can do calculations, and you see that the effects strongly depend on the temperature. It's not 0.5, it's 0.5 at a much lower temperature, but at the actual temperature, up here, we have a much larger correction, a correction of 0.3. So now I want to skip through the next slides, but what this means is that their measured value has to be corrected by this much to get to the gas phase value at 0 Kelvin. And if you do this, you end up with 2.67, which, if you remember, is exactly the value. Okay, this is a lot. We can very well understand how all of this worked. But their essential problem was that they did not use an accurate method for the correction, but they used their GFN1 here, which is very bad. And by using a combination of this highly accurate wave function theory of DFT for the solid and for the molecule, lots of functionals, and these very fast semi-empirical methods, which are fast enough to simulate this for 50 nanoseconds, we could really kind of follow through, see what their mistake was, and understand even how this mistake happens, because it actually has to do with the fact that this molecule opens up at this high temperature, and then you get a lot of conformers with a much larger distance. And this little bump then shifts the average by the 0.3.
I think Greg brought up that point of self-rotation distortion in the comments.
Sorry, could you repeat that, please? I didn't understand that.
Yeah, I think Greg commented about the rotation distortion.
I didn't. I still didn't understand that. Maybe afterwards. Let me finish. I'll be finished in 5 minutes, and then we can talk about this again. Okay? I just want to get it over. Yeah. Okay, so and this was a long story, and the short message. The message is actually DFT connects these two regimes. You have these highly accurate simulations where you can really rely on the result and trust the result, but you can't use this for simulations because you have no chance. Every single calculation takes you an hour, so you cannot do 10,000, 100,000 steps. But because of DFT, we have this bridge between these accurate methods, which we can use to test and parameterize DFT, and then we can use DFT again to parameterize and test these more efficient methods like GFN. And then we can do a GFN simulation for this large system where we know that the potential shape that this fast method gives us is reasonably accurate with respect to the high-level method. And then we basically know by this chain of proof from very robust high-level calculations through DFT and finally our semi-empirical methods that the simulation we do at this cheap level is still reasonable. There's pitfalls with this, and you need to be very careful when you make this kind of conclusions from one level to the other. But my point here is that without DFT, we wouldn't even be able to make this, because you need something intermediate between this very fast and this very accurate. And this is DFT, and this is a very important role DFT often takes in these studies where it's not used just to be applied to this special reaction or this barrier or this reaction path, but it kind of connects these regimes of highly accurate and very efficient methods. And nowadays, I guess I shouldn't put empirical MO here. There should be ML if this is or NNP if you want to make this a modern 2025 lecture, because the parameters now you calculate. There was just a few days ago, they published a huge database with millions of calculations, DFT calculations on 25 million molecules. And this is kind of marketed towards the machine learning community. This is what you can use to train your neural network potentials. Right, so nowadays, I guess there's another point here. And with this, we are at the, I should have removed the animations here. We're at the end of the lecture. Today, we just talked a little bit about chemistry, a little bit of the Hohberg cone. We will go into these in more detail in the next lecture about compchem again. We talked a little bit about functionals, but again, we will talk about this in much more details in the upcoming lectures. And I hope that in 10 lectures or so, you all will have a kind of a robust understanding of DFT. Its weaknesses and its strong points, both are important. Okay, this was it. I can finally stop sharing, or are there questions regarding the slides? Now is your chance again, please.
Yeah, and I have a question. Just a quick one. Sorry.
Yeah. Whoever spoke first, please go first.
Sorry. I don't know who I interrupted there. The paper you presented, that was in 2021, right?
Yeah, I think so, yes.
There was a quick comment at the end in the methods saying that you ran the MD on just one core of a CPU.
Yes.
How does that speed translate to, say, what you can run now using maybe even GPUs for MD?
It's then 20 atoms, so I just needed one CPU. That's the reason. And then, I during the simulations, I saw that this value converges very slowly. And then I extended the time on. And I think 1 nanosecond I thought was sufficient, but in the end, it changed quite a bit until 20, 30 nanoseconds. I ended up running it for 50 nanoseconds to be absolutely sure. And this has to do with the fact that the molecule opens up and closes, and this just is an improbable process that takes time. But if you wanted to do this for longer nowadays, there's no problem. I guess with a GPU, you could speed up this calculation maybe a factor of 10, maybe a factor of 100. I'm not so experienced with using GPUs for this. The Banwart group in Aachen is like promoting this, doing GFN on GPUs. But I think it's easily possible for such a system nowadays with this or with even better methodology to go into the microsecond regime. Maybe even milliseconds.
Sure,
so
thank you.
It's not a big issue. The question is what phenomenon you can kind of observe, right? And the stuff that gets really interesting, which happens on a millisecond timescale, usually happens in big molecules. You say protein, but then it's not the same question because then you have all these atoms. You need the water, and then simulations have other kind of bottlenecks. I hope that was clear.
Right. Yeah. Thank you so much.
Welcome. I think we had one more question.
I'm gonna more comment on. I think it might be useful if there would do some exercises, relatively simple exercises. I guess I know like the computational part that everybody likes is really different. That's what but I definitely think that would be very useful for this mini series.
Okay, thank you.
Hi, Jane. Thanks for so much for this presentation and this initiative. I have a very small question. Like how you were able to see the discrepancies in this DFT data and you decided to work on it. Like how were you able to question that published work? Generally, on the published work, we don't question it. We think like this is a benchmark because it has been audited before by so many people, so we just thought okay, it should be validated. We just try to replicate it basically, but we don't question it on the very first time. So why did you think there is some problem with the data?
So two things I want to say to that. It's a very good question. So to directly answer your question first, intuition. Like Stefan Grimme, if you are in the business for as long and you see a difference between two functionals like PB0 and M062X, which are very similar in what they are, and they never give such a huge difference. So this was the first thing which seemed fishy. So like this cannot be true. Let's rerun the calculation to be sure. And this was the first thing we did. And yes, it confirmed our suspicion that we can't reproduce their value. And the other thing is, I understand what you're going at when you say we should take published stuff for benchmark because it has been reviewed. But having been in the business for that long, usually the review is not perfect. So lots of stuff that gets published, in particular, since everybody nowadays runs calculations, you don't always have a referee in these publications, which is an expert in calculations. It's possible nowadays because there's cool programs which take much of the work off of you to run black box calculations, but many people who do this now are not specialists. So don't blindly trust papers just because they are published. They are more trustworthy than what you have just done on your own computer in 5 minutes. But if you do your calculation and you double and triple check and you still diverge from what they did, then I would say you should trust your work and question the paper too.
Okay, thanks for the kind advice. So basically, we should first like research our own functionals, like how it should be and how the prediction should come out, like estimate range, and then like we should try to replicate something if we are interested, basically.
Yes, replication is key. In particular, with an experiment, nobody has a GED machine here at home. I guess none of you either. So this is special stuff, and you can publish as many details as you want. It's just not possible to reproduce these things. But with DFT, everyone on their home computer can run Orca nowadays and can run a PBE0 or M062X optimization of such a molecule. It maybe takes a couple of minutes, but you can certainly do it. And that means publications should also provide all the details necessary to reproduce the data. This is something, when I do a review, this is something I always write. Please publish the geometries, please publish the input files, so I can reproduce the calculations, because this is really the easiest way to note an error, to notice that something is wrong. Everyone can reproduce these, so it should be possible, it should be made possible by the authors with the supplementary material to reproduce the calculations. Because if I publish something and it's wrong, I want to know about it. So I'm happy if somebody writes a comment on my paper and says, well, you did something wrong there. Right? So usually people that you approach these people. But I think reproducibility is something, because everybody can run a DFT calculation, it's a big issue, much bigger than running an experiment. Nobody has a GED or an MR machine. So the only thing we need to do is to provide the data. Okay?
Okay.